Have you ever noticed those spiral patterns, like in sunflowers or seashells?
Mm.
Even the stock market seems to follow them.
Yeah. It's fascinating, isn't it?
I feel like it's not magic, though. It's got to be something mathematical, right?
It is. You're actually seeing the famous Fibonacci sequence in action.
Oh, yeah. The Fibonacci sequence.
It's a simple pattern, really. Each number is just the sum of the two before it.
1, 1, 2, 3, 5, 8, and so on.
Exactly. And what's really mind-blowing is that this sequence pops up everywhere.
Yeah, I've heard that. Everywhere.
Pretty much. From the arrangement of petals on a flower to the structure of galaxies, even.
Seriously. Galaxies, too.
You'd be surprised. The Fibonacci sequence is a beautiful example of how a simple mathematical concept can have these huge implications in tons of fields.
So for this deep dive, we're going to explore this sequence.
Definitely. We'll go beyond just the basics, explore its mathematical beauty, its connection to the golden ratio, even its potential role in quantum mechanics.
Okay, we all know the basic pattern.
Yeah.
1, 1, 2, 3, 5, 8. But what makes it so special? What's all the hype about?
One of the key reasons is its close relationship with another mathematical marvel, the golden ratio.
Golden ratio.
Yep. It's often represented by the Greek letter phi, and its value is approximately 1.618.
Okay.
Now, as you go further down the Fibonacci sequence, the ratio between consecutive numbers gets closer and closer to this golden ratio.
So the golden ratio is like a hidden target.
Exactly. Like the Fibonacci sequence is always approaching it.
I see. And this golden ratio, it's not just some random number, is it?
Definitely not. It shows up all the time in nature and art, often associated with aesthetically pleasing proportions, actually.
Really? Like where?
You see it in the proportions of the human body, the arrangement of leaves on a stem, even the design of ancient Greek architecture.
Wow. Okay, so how does this golden ratio actually emerge from the Fibonacci sequence? We're just adding numbers, right? Where do these irrational numbers come from?
That's where it gets really interesting. There's a formula called Binet's formula that lets us calculate any Fibonacci number directly without having to go through the whole sequence.
Oh, wow.
And guess what? This formula explicitly uses the golden ratio and its conjugate.
Wait, hold on. Conjugate. We're getting a bit technical here.
Sure. The conjugate of the golden ratio is simply a related irrational number. It's often denoted as Ci, and its value is approximately 0.618.
Okay.
It's essentially the same expression as the golden ratio, but with a minus sign in front of the square root of 5.
I see. And how do these irrational numbers combine to produce whole numbers in the Fibonacci sequence?
That's the beauty of Binet's formula. It states that the nth Fibonacci number is equal to phi to the power of n minus pi to the power of n, all divided by the square root of 5. Now, because the magnitude of Ci is less than 1, its powers get smaller and smaller as n increases, eventually becoming negligible. For large Fibonacci numbers, the formula basically boils down to phi to the power of n divided by the square root of 5, which miraculously gives us a whole number.
So the contribution of the conjugate just fades away.
Exactly. It's like the golden ratio becomes the dominant force.
Interesting.
It's a beautiful example of how seemingly complex irrational numbers can lead to these simple whole numbers through this intricate interplay within the formula.
That is pretty cool. But we've been talking about adding numbers, a discrete process. How do we go from that to a continuous solution? You mentioned something called the Lambert W function earlier.
Yes. That's a great question. The Lambert W function comes into play when we start dealing with more complex growth models, ones that go beyond the simple Fibonacci recursion.
Okay.
Imagine a population of rabbits, but their reproductive rate isn't constant. It depends on the current population size.
Due to limited resources.
Exactly. This type of scenario leads to equations that involve a variable both as a base and an exponent, something like x times e to the power of x. Oh, I vaguely remember those kinds of equations from calculus.
They're tricky, aren't they?
Yeah, they weren't easy to solve.
Exactly. And that's where the Lambert W function comes in. It's designed to solve those tricky equations and provides us with explicit solutions for those more realistic growth models.
So it helps bridge the gap between the discrete world of adding numbers and the continuous world of growth and change.
You got it. The Lambert W function helped us understand how the discrete nature of the Fibonacci sequence can actually translate into these continuous dynamics that we observe in nature, like the spiral growth of a seashell or the branching pattern of a tree.
Wow, that's amazing. We're starting to see how this seemingly simple sequence connects to these complex growth patterns and advanced mathematical functions. But how does all of this relate to quantum mechanics? You mentioned that earlier, and it's been bugging me.
That's where things get really interesting. Some research suggests that Fibonacci-like sequences might actually play a role in the energy level spacing of certain quantum systems.
For example, imagine an electron in an atom.
Right.
It can only exist at specific energy levels, and sometimes those energy levels are spaced according to Fibonacci-like ratios.
So we're talking about the very foundation of matter, the quantum world potentially exhibiting this Fibonacci pattern.
It's a fascinating possibility, and researchers are still actively exploring this connection.
Wow.
Some studies have even observed Fibonacci-like sequences in the diffraction patterns of quasicrystals, which are materials with a unique atomic structure that's ordered but not periodic.
That's amazing. We started with a simple sequence, and now we're talking about quantum mechanics and the structure of matter. Is there any specific research or examples that delve into this connection further?
Absolutely. There's a paper that explores the quantum effects of Lucas numbers.
Lucas numbers. Are those related to the Fibonacci sequence?
Oh yeah, they're very closely related. The Lucas sequence follows the same rule, adding the previous two numbers.
Nice.
But it starts with different initial values, 2 and 1 instead of 1 and 1. This slight difference leads to a different sequence, but it shares the same underlying mathematical structure and exhibits many similar properties.
So what's the connection between Lucas numbers and quantum mechanics?
This paper suggests that Lucas numbers might represent excited states in a quantum system.
Excited states.
Yeah, think of it like an electron in an atom jumping to a higher energy level when it absorbs energy.
Okay.
The Lucas numbers, in this context, might describe the energy levels of those excited states.
So we're saying that the energy levels in the quantum world could potentially be described by these number sequences. That's quite a leap from counting sunflower seeds.
It is a bold idea, but the mathematical framework seems to support it. They even explore potential connections to hyperbolic geometry and something called the Selberg trace formula, suggesting that these number sequences might have a geometric interpretation in the quantum realm.
Okay, hold on. Hyperbolic geometry and the Selberg trace formula. Those are not terms you hear every day. Can you try to break those down for us a bit?
Okay. Imagine a saddle-shaped surface. That's a simple way to visualize hyperbolic geometry. It's a non-Euclidean geometry where parallel lines diverge, unlike our familiar flat plane.
Okay.
Now, the Selberg trace formula is this powerful tool that connects the geometry of these hyperbolic surfaces to the frequencies at which waves can vibrate on them.
So are we saying that these number sequences, like Fibonacci and Lucas numbers, might be connected to the music of the quantum world?
It's a beautiful analogy, and it highlights this profound interconnectedness between seemingly different fields. Number theory, quantum mechanics, and geometry all intertwined in ways we're only beginning to understand.
That's pretty incredible. We start with a simple number sequence, and now we're talking about the fundamental principles of growth, the structure of matter, even the quantum world.
Yeah, and we're just scratching the surface. There's still so much to explore and uncover about the Fibonacci sequence and its implications. Let's delve a bit deeper into how this sequence shows up in biological systems.
Okay, so let's shift gears a bit and talk about those biological systems. Where do we see the Fibonacci sequence popping up there?
The Fibonacci sequence and the golden ratio are practically everywhere in nature.
Like where? Give us some examples.
You mentioned sunflowers earlier.
Yeah, sunflowers are pretty cool. What about them?
Sunflowers are a classic example. If you look closely at the arrangement of the seeds in a sunflower head, you'll notice they spiral outwards in both clockwise and counterclockwise directions. And what's fascinating is that the number of spirals in each direction is almost always 2 consecutive Fibonacci numbers.
Really? What?
Like 21 and 34? Or 34 and 55?
No way. So nature is literally counting using the Fibonacci sequence.
It is. It's called phyllotaxis. This arrangement allows the sunflower to pack as many seeds as possible into the flower head.
So it's like nature's way of optimizing.
Exactly. It maximizes its reproductive potential.
Wow, that's pretty amazing. So there's an evolutionary advantage to this pattern.
Oh, absolutely. The golden angle, which is closely related to the golden ratio, plays a big role here. By arranging the seeds at this specific angle, the sunflower avoids any direct overlap, ensuring that each seed gets optimal exposure to sunlight and nutrients.
That's pretty cool. Nature is not just beautiful, it's incredibly efficient, too.
It is.
Are there any other examples of this Fibonacci magic? Like in other plants?
Tons. The number of petals on a flower is often a Fibonacci number.
Oh, yeah.
Think about lilies.
How many petals do they have?
3. Buttercups have 5. Delphiniums often have 8. Daisies, often 34 or 55 petals.
I never noticed that.
It's everywhere. And it's not just limited to flowers either. Fibonacci patterns in the arrangement of leaves on a stem, the branching patterns of trees, even the spirals of a pine cone.
This is making me want to go outside and start counting petals. But why this specific sequence? Are there any mathematical reasons why nature seems to prefer Fibonacci?
There are a few theories. One idea is that the golden angle, the one derived from the golden ratio, provides the most efficient way to pack elements in a spiral, maximizes space and resource distribution.
I see.
Another theory is that these patterns emerge from the dynamics of plant growth hormones, which might naturally follow Fibonacci-like rules.
So it could be a combination of efficiency and the underlying mechanisms of biological development.
Precisely. And it's not just plants either. We also see Fibonacci spirals in the animal kingdom. The shells of mollusks, like nautiluses and some snails, follow a logarithmic spiral, one that closely approximates the golden spiral, which is a spiral whose growth factor is, you guessed it, the golden ratio.
Oh, wow. I've always loved nautilus shells.
Yeah.
The shape is so beautiful.
And their growth pattern is fascinating. As the nautilus grows, it adds new chambers to its shell, and each chamber is proportionally larger than the previous one, following the golden ratio.
So it keeps that same shape.
Yeah. This allows the nautilus to maintain its shape and buoyancy as it grows.
That's so cool. It's amazing to think that this mathematical sequence is built into life itself, guiding growth and development across so many different organisms.
It is. The Fibonacci sequence and the golden ratio offer a peek into the elegance and efficiency of nature's design.
It's not just visual patterns, though, right? Does this sequence play any role in other biological processes?
Yeah.
Like at the cellular level or even smaller?
That's a great question. Scientists are definitely exploring the role of Fibonacci-like patterns in various biological processes. Some studies suggest that the arrangement of microtubules, which are part of the cell's internal skeleton, might follow Fibonacci-like spirals, and this could influence cell division and growth.
So the Fibonacci sequence could be at play even at the microscopic level, influencing the very building blocks of life.
It's a possibility, and it really shows how this simple mathematical concept might have far-reaching implications across different scales of biological organization.
This is remarkable. It seems like the Fibonacci sequence is more than just a pretty pattern. It might be a fundamental principle that underpins the structure and growth of life itself.
It really might be, and that raises even more questions. What if this sequence reflects some deeper computational principle at work in the universe?
Oh, wow.
Guiding not just biological systems, but also physical phenomena, even at the quantum level.
Now you're really making me think. This whole deep dive has been amazing. We started with a simple sequence and ended up contemplating the fundamental nature of reality.
It has been quite a journey.
It's truly inspiring to see how a single mathematical concept can lead to so many profound insights and open up so many new avenues for exploration.
It really is.
All right, so let's shift back to the math a little bit. We keep talking about this Lambert W function.
Yes.
And it sounds pretty important, but I have to admit, it's still a bit of a mystery to me.
It's a pretty powerful tool, and it helps us understand how the Fibonacci sequence can actually describe continuous growth processes.
Yeah, because it seems like it's all about discrete steps of addition.
Right.
So remind me again, how does that work? Like, where does the Lambert W function even fit in?
Remember those equations, where the variable appears both as a base and an exponent, like x times e to the power of x.
Yeah, vaguely.
Those are the kinds of equations that we get when we're dealing with growth that's not just simple and constant,
Okay.
but it depends on the current state of the system.
Like those rabbit populations we talked about,
Yeah.
where their reproduction rate changes based on how many rabbits there are.
Exactly. And those equations are super hard to solve using our normal algebraic methods.
Yeah, I can imagine.
That's where the Lambert W function comes in. It's specifically designed to tackle those kinds of equations, and it gives us explicit solutions for those more complex growth scenarios.
So it's like a special tool for those hard math problems.
Yeah, that's a great way to put it. And the really cool thing is that it allows us to connect the discrete world of the Fibonacci sequence with the continuous world of growth and change, and those feedback loops that we see in nature.
Okay, so let me see if I understand this. We start with the Fibonacci sequence, this simple pattern of adding numbers.
Yeah.
Then we find out it's connected to the golden ratio, which pops up everywhere in nature.
Right.
But then when we want to look at more realistic growth models, where things aren't so neat and tidy, we need this more powerful tool, the Lambert W function, to really make sense of it.
Exactly. You got it.
Yeah.
The Lambert W function is like a bridge. It helps us see how the elegance of the Fibonacci sequence translates into the messy but fascinating complexity of real-world growth. It's a good reminder that math isn't just about abstract formulas. It's a language for understanding the universe and all its intricacies.
Yeah, totally. And speaking of messy complexity, we also talked about quantum mechanics and how the Fibonacci sequence might be hiding in there, too.
Right.
Can we talk about that a bit more? It still feels like a crazy idea to me.
It is a mind-blowing concept, but there's more and more evidence suggesting that certain quantum systems, like the ones dealing with the very building blocks of matter, they might exhibit energy level spacing that follows Fibonacci-like patterns.
So it's like those energy levels are quantized according to the Fibonacci sequence.
Yeah.
As if the universe is playing by these mathematical rules.
Yeah.
Even at the tiniest level. I love that.
What's really fascinating here is that these papers, they give us a glimpse into how math can be both beautifully ordered and surprisingly chaotic.
Yeah.
So we'll be exploring Fibonacci sequences, which are way more than just pretty spirals that you see out in nature. They have real applications in design coding, even cryptography, random polynomials. Are their roots truly random, or is there like a hidden pattern there?
I am intrigued already.
Get ready for some aha moments.
So the paper Fibonacci, partial sums tricks, hints that there's more to it than meets the eye. What's going on there?
So this paper dives into calculating partial sums of the Fibonacci sequence, and it's not just adding the numbers up the long way. There are these really elegant shortcuts.
Okay.
Almost like mathematical magic tricks.
Oh, I love a good magic trick.
Right.
Give me an example.
Okay, so imagine you want to add up the first 10 Fibonacci numbers.
Okay.
You could do it manually, but here's the trick.
Yeah.
You take the 7th Fibonacci number, which is 13, multiply it by 11, and you get 143.
Okay.
That's the sum of the first 10.
No way.
Yeah.
That's so much faster
Isn't that cool?
than adding them all up.
Yeah.
I'm starting to see why these tricks will be useful. What's the underlying principle here?
Yeah.
Is it just a coincidence?
No, not at all. This trick and others like it stem from the recursive nature of the Fibonacci sequence.
Okay.
So remember, each term is built from the ones before it.
Yeah.
And this recursive structure creates predictable relationships between different parts of the sequence that we can exploit to make these calculations faster.
So these shortcuts aren't just random tricks.
Yeah.
They're based on the inherent structure of the sequence.
Yeah.
That's really cool.
Pretty neat.
Now let's jump to this other paper.
Okay.
Binary sequences meet the Fibonacci sequence.
Right.
It sounds like a clash of worlds.
Yeah.
But I have a feeling you're going to tell me they're actually connected.
You are absolutely right.
Okay.
This paper explores how the Fibonacci sequence, which seems so analog and continuous, can be related to the digital world of binary code with its ones and zeros.
Okay.
And this connection has some really important implications for fields like cryptography and computer science.
Okay, you've officially piqued my curiosity. Tell me more about this connection.
Okay.
It seems counterintuitive that something as organic as the Fibonacci sequence would have anything to do with the rigid world of binary.
The key lies in looking at the Fibonacci sequence modulo 2.
Modulo 2.
Modulo 2.
Okay.
In simpler terms, we're only focusing on whether each Fibonacci number is odd, or even U.
Okay.
If it's odd, we represent it with a 1. If it's even, we use a 0.
Okay.
And guess what? When you do this, you start to see patterns emerge.
Yeah.
That can be expressed as binary sequences.
So it's like we're translating the Fibonacci sequence into a digital language.
Yeah.
That's pretty mind-blowing. But why is this relevant? What can we do with this connection?
One exciting application is in cryptography, the art of secure communication. And the paper even introduces this really intriguing sequence called the Thumor sequence, which is built by repeatedly substituting one pattern for another.
Right.
It's connected to the Fibonacci sequence modulo 2. But it has its own unique properties that make it really valuable for creating secure codes.
Whoa.
Yeah.
So we've gone from Fibonacci spirals in nature to secret codes in the digital world.
That's right.
Math is full of surprises.
It is.
But before we dive deeper into the Thumor sequence, I want to understand this modulo 2 idea a bit better.
Okay.
It feels like a bridge between the continuous and the discrete.
You are right on the money.
Okay.
So thinking in terms of modulo is like switching from a world of smooth, infinite possibilities to a world of distinct countable units.
Okay.
And it's the shift from the continuous to the discrete that allows us to connect the Fibonacci sequence to the binary world.
Ah, I see.
Yeah.
So we're imposing a digital lens
Uh-huh.
on a continuous concept.
Exactly.
That's fascinating.
Yeah.
But how does this modular thinking apply to something as complex as cryptography?
So in cryptography, we often deal with very large numbers
Oh.
and complex calculations. And by working modulo a specific number, we can reduce these large numbers to smaller, more manageable ones within a finite system.
Okay.
And this makes calculations easier and faster, which is crucial for encryption and decryption algorithms.
Okay.
It's like creating a secure mathematical playground
Right.
with clearly defined boundaries.
And it's such a cool way to think about it. So we're not just simplifying the math, we're also creating a more secure environment for information exchange.
Exactly.
I'm starting to see the power of this discrete approach.
Yeah.
And this brings us to another paper that you shared
Okay.
on the distribution of the multiplicative order modulo n.
All right.
Now, this one might sound intimidating.
It does sound a little intimidating.
Trust me, the core concept is really quite elegant.
It is.
Okay, I'm all ears. But before we jump into multiplicative order,
Yeah.
can we take a quick detour back to the Thumor sequence?
Excellent point.
I'm really curious about its role in cryptography
Okay.
and how it connects to Fibonacci.
Let's explore the Thumors a bit more before we tackle multiplicative order.
I'm glad we're circling back.
Yeah.
So you mentioned that the Thumor's sequence is built by substituting patterns.
Yes.
Can you give me a visual?
Sure.
Like, how does this substitution process actually work?
Absolutely. Imagine you start with the digit 0,
Okay.
and then you replace every 0 with the pattern 0, 1, and every 1 with the pattern 10.
Okay.
So 0 becomes 0, 1, then 0, 1 becomes 0, 1, 0,
Yep.
then 0, 1, 0 becomes 0, 1, 0, 1, 0, 1, and so on.
Wow. I'm already seeing how this could generate incredibly complex sequences.
Yeah.
But why is this particular sequence so special for cryptography?
What makes the Thumor sequence so valuable is that it's both predictable and unpredictable at the same time.
Okay.
It's predictable in the sense that it's generated by a simple rule, but it's unpredictable in that it doesn't have any obvious repeating patterns.
Okay.
And this lack of repetition is crucial for creating codes that are difficult to crack. It's like a secret code hidden within a seemingly simple pattern.
So it's like controlled chaos.
Yes.
We have this underlying order, but the resulting sequence appears almost random.
Right.
I can see how that would make it incredibly difficult for someone to decipher a message encrypted with the Thumor sequence.
Exactly. It's like creating a maze with a secret pattern that only the intended recipient can decipher. And what's even cooler is that this sequence, which seems so digital and modern, is intrinsically linked to the ancient concept of the Fibonacci sequence.
That's what blows my mind about math.
Yeah.
It's like we're discovering these hidden connections that have always existed, but we're just now starting to understand them.
Totally.
Okay, now I'm really ready to tackle multiplicative order.
All right.
I'm ready to face my mathematical fears head on.
You got this. Multiplicative order might sound intimidating, but it's really about understanding cyclical patterns in multiplication.
Okay.
Think of it like a clock.
Hold on, let me guess.
Yeah.
We start at 1 on the clock
Okay.
and keep multiplying by, say, 2. We get 2, 4, 8.
Right.
And eventually we cycle back to 1.
Yeah.
Is multiplicative order telling us how many steps it takes to complete that cycle?
You are exactly right.
Okay.
It's like a clock for multiplication, but instead of hours, we're looking at the steps it takes to cycle back to our starting point when multiplying by a specific number.
Okay, that makes so much more sense.
Yeah.
But how does this connect to Fibonacci sequences?
Yeah.
Or the Thumor sequence?
All right.
We seem to be hopping between different mathematical worlds here.
That's the beauty of this deep dive. It's all about connecting seemingly disparate concepts.
Yeah.
But in this case, multiplicative order helps us understand how values related to the Fibonacci sequence, like the Zeckendorf sum of digits function,
Or 4.
are distributed when we look at the modulo M.
Oh.
It's like analyzing the footprints of Fibonacci in a modular world.
Wait, hold on. You've thrown another new term at me. The Zeckendorf sum of digits function. Can you unpack that for me?
Of course. Remember how we talked about representing any number as a sum of Fibonacci numbers?
Yes.
The Zeckendorf sum of digits function tells you how many Fibonacci numbers you need to add up to get that particular number.
Okay.
So for example, let's say you have the number 10.
Okay.
Its Zeckendorf representation would be 8 plus 2,
Okay.
which uses 2 Fibonacci numbers.
Okay, that makes sense.
Yeah.
So it's like finding the most efficient way to build a number
Yeah.
using Fibonacci blocks.
Exactly.
But how does this function relate to multiplicative order?
Okay.
We're analyzing its distribution modulo m.
Exactly. So by applying multiplicative order to the Zeckendorf function modulo m, we're essentially looking at how these Fibonacci building blocks
Okay.
are spread out when viewed within a specific modular system. And it gives us insights into the deeper structure and patterns within these sequences.
My brain is doing some serious gymnastics right now.
It's a workout.
But in a good way. I love how we're connecting these seemingly abstract concepts.
Yeah.
So we've gone from Fibonacci tricks to binary codes to multiplicative order. It's like we're peeling back the layers of a mathematical onion.
Yeah.
And each layer reveals a new and fascinating connection.
I love that analogy. And believe it or not, there's another layer to explore.
Okay.
Remember that paper on random polynomials? It might seem like a completely different topic.
Yeah.
But it actually ties into this theme of order versus chaos that we've been discussing.
Okay. I'm ready for the next layer.
Okay.
Bring on the random polynomials.
Welcome back to our deep dive.
I'm still trying to wrap my head around the idea that Fibonacci sequences can be translated into binary code.
Right.
It's like we're bridging the gap between the natural world and the digital world.
You got it. And that's what's so exciting about mathematics.
Yeah.
It helps us discover hidden connections between seemingly unrelated things. But before we move on to random polynomials, I want to make sure we highlight the practical applications of these ideas.
Yeah.
We've talked about cryptography,
Right.
but Fibonacci sequences and recurrence relations, they pop up in so many other fields.
Oh, I'm all ears. Give me some real-world examples. How does this math actually impact our lives?
Let's start with design and architecture.
Okay.
Have you ever noticed that certain proportions just feel more pleasing to the eye?
Yes. Like some buildings or paintings just seem more balanced and harmonious than others?
That's where the golden ratio comes in.
Yeah, okay.
So it's the special number, approximately 1.618,
Okay.
that's closely tied to the Fibonacci sequence.
Okay.
So if you divide a Fibonacci number by the one before it, the result gets closer and closer to the golden ratio as you move further down the sequence.
So the Fibonacci sequence is like a blueprint for the golden ratio.
You could say that.
But how does this translate into aesthetics?
So the ancient Greeks believed that the golden ratio represented perfect proportions.
Okay.
And they incorporated it into their architecture and their art.
Interesting.
The Parthenon, for example, is full of golden ratio proportions.
Wow.
And it's not just an ancient idea. Modern designers and architects still use the golden ratio to create aesthetically pleasing spaces, websites, even product designs.
Wait, so you're telling me that math can actually make things look prettier?
It's not that math makes things prettier,
Okay.
but it provides a framework for understanding why certain proportions feel more balanced and harmonious to us. And the golden ratio might actually reflect the fundamental principle for efficiency and growth in nature,
Okay.
which is why we see it reflected in so many biological structures, like the arrangement of petals in a flower or the spiral of a seashell.
So it's like nature is following a mathematical blueprint, and the golden ratio is one of its key building blocks.
Yeah.
It's amazing how this simple concept can have such profound implications.
It is.
Okay, so we've got design and architecture covered. What other fields does this math influence?
Let's talk about engineering.
Oh, okay.
Remember those polynomials we mentioned? They're not just abstract concepts you suffered through in algebra class. They're incredibly powerful tools for modeling real-world phenomena.
Wait, polynomials can describe things in the real world.
Yeah.
I always thought they were just these algebraic puzzles.
Oh, they're much more than that.
Okay.
So engineers use polynomial equations to design everything from bridges and buildings to airplanes and spacecraft.
Wow.
So for instance, imagine you're designing a bridge.
Oh.
Engineers use polynomial equations to calculate the stresses and strains on different parts of the bridge, making sure it can withstand the weight of traffic and environmental factors.
So it's like using math to make sure the bridge doesn't collapse.
Exactly.
That's a pretty important job.
It is. And the roots of these polynomials, the values that make the equation equal to 0, they represent critical points where the behavior of the bridge might change.
Okay.
Polynomials allow engineers to predict and control the behavior of these complex systems, ensuring that they're safe and functional.
But how do engineers deal with the uncertainties of the real world?
That's a great question.
Things aren't always as neat and predictable as mathematical equations.
Right, and that's where the idea of random polynomials comes in.
Right.
Sometimes engineers have to deal with factors that are inherently unpredictable, like wind gusts or variations in materials.
Right.
Random polynomials help us model these uncertainties and assess the overall reliability of a structure.
So it's like we're acknowledging that there's always an element of chaos in the real world.
Yeah,
And we're using math to understand and manage that chaos.
exactly.
That's pretty profound.
It is, and this brings us back to that paper on the number of real roots of random polynomials.
Good.
It's exploring how we can predict the behavior of these complex systems even when randomness is involved. It's like finding patterns within chaos.
Okay, my mind is officially blown.
Yes.
We've gone from Fibonacci spirals in nature to secret codes to engineering marvels, and now we're talking about predicting chaos with math.
I know, right?
I'm starting to see how these concepts, which seem so different at first, are all interconnected.
Exactly. And this connection is rooted in the idea of discrete versus continuous mathematics.
Okay.
Remember how we talked about modular thinking and shifting from a world of infinite possibilities to a world of distinct units?
Yes. It was like imposing a digital lens on a continuous concept.
That's a perfect way to put it.
Yeah.
And this distinction between discrete and continuous
Right.
is fundamental to many areas of math and its applications.
Okay.
So, for example, computer science relies heavily on discrete math, while calculus and physics often deal with continuous functions.
So it's like we have these two different lenses for looking at the world.
Yes.
And each lens reveals different patterns and relationships.
That's a great way to think about it.
But how does this connect to Fibonacci sequences or random polynomials?
So Fibonacci sequences are a great example of a concept that bridges the gap between discrete and continuous. We can analyze them as a continuous spiral, but we can also break them down into discrete units and explore their properties modulo em.
Okay.
Random polynomials also blur this boundary.
Okay.
We're dealing with continuous functions,
Yeah.
but we're trying to understand how they behave in the face of discrete, unpredictable events.
I'm starting to see how this distinction between discrete and continuous is more of a spectrum than a clear-cut divide. And the math we've been discussing falls somewhere along this spectrum.
You've got it, and that's what makes this deep dive so fascinating. We're exploring concepts that live in this liminal space between order and chaos, between the continuous and the discrete.
Okay, so we've covered design, architecture, engineering. What other real-world applications can you throw at me?
Let's talk about forecasting.
Okay.
Recurrence relations, the idea that a term depends on the ones before it,
Right.
are the backbone of many forecasting models.
Okay.
And we see them in finance economics, weather prediction, even population dynamics.
So when I check the weather app, there's a bit of Fibonacci lurking behind those predictions.
You could say that, of course, weather forecasting is incredibly complex.
Right.
But the fundamental idea is to use past data to predict future trends. And recurrence relations provide a mathematical framework for capturing those trends and making reasonable predictions.
That makes sense. But what about finance?
Okay.
I've heard that some stock traders use Fibonacci numbers to analyze the market. Is there any truth to that?
Some traders believe that Fibonacci numbers and ratios, particularly the golden ratio, can help them identify potential support and resistance levels in stock prices.
Interesting.
They look for patterns in price movements that align with these ratios to predict future price swings.
Okay.
It's a controversial approach, but it shows how people are trying to find order within the seeming chaos of the market.
That's fascinating. So it's like they're using math to try to decode the stock market, which seems pretty unpredictable.
Yeah.
But is there any scientific evidence to support this approach?
The effectiveness of Fibonacci analysis in finance is a hotly debated topic.
Okay.
Some studies have shown correlations between Fibonacci ratios and market movements, but others have dismissed it as mere coincidence. It's an area where subjective interpretation plays a significant role.
Yeah.
Ultimately, predicting the stock market with perfect accuracy is impossible. There's just too many variables at play.
So it's more of an art than a science.
Yeah, you could say that.
But regardless of its effectiveness, it's interesting to see how traders are applying these mathematical concepts to try to make sense of the financial world.
Exactly. It highlights the human desire to find patterns and make sense of seemingly random events.
Right.
We're constantly searching for order within chaos,
Yeah.
and math provides us with powerful tools for that exploration.
Okay, so we've covered design, engineering, forecasting, finance. Is there anything else we can add to this list of real-world applications?
Let's not forget about coding.
Oh, yeah, coding.
Binary sequences, which we explored in relation to Fibonacci, Right. The foundation of computer programming. Understanding how information can be represented and manipulated using binary is essential for building software, designing algorithms, creating digital technologies.
Every time I use my computer or smartphone, I'm interacting with the world of binary sequences.
You are.
It's crazy to think that something as simple as a sequence of ones and zeros can underpin such complex technologies.
It is, and the connection between Fibonacci sequences and binary code highlights the deep relationship between math and computer science.
Absolutely. Okay, my brain is officially full.
I know, right?
We've covered so much ground today.
We have, but we're not quite finished yet.
Oh, there's more.
In the final part, we'll wrap up our deep dive by reflecting on what we've learned and exploring some of the bigger questions that this journey has raised.
I can't wait. This has been an incredible exploration of the power and beauty of math, and I'm excited to see where we go next.
Welcome back to the final part of our mathematical deep dive.
It's been quite a journey, hasn't it?
We've explored everything from Fibonacci spirals in nature
I know it's a lot.
to the unpredictable world of random polynomials.
My head is still spinning from all the connections we've uncovered.
Yeah.
I feel like I've gained a whole new appreciation for the power and beauty of math.
That's the magic of these deep dives.
Yes,
They help us see the world through a different lens, revealing the hidden patterns and connections that underpin reality.
So as we wrap up this incredible exploration,
Yeah.
what are some of the key takeaways
Okay.
you'd like our listeners to remember?
I think the most important insight is that math is more than just a collection of formulas and equations. It's a way of thinking,
Right.
a language for understanding patterns and relationships that exist everywhere.
Yeah.
And we've seen how these patterns manifest in the natural world, in the digital realm, and even in seemingly random events.
It's like math is the underlying code of the universe.
Exactly. And what's so fascinating is that we're constantly discovering new connections and applications for these mathematical concepts. Who would thought that the Fibonacci sequence, something observed in ancient times, would have relevance in modern cryptography or stock market analysis?
It makes you wonder what other mathematical secrets are out there
Right.
waiting to be discovered.
Absolutely. And that's what makes math so endlessly fascinating.
Hmm.
It's a never-ending journey of exploration and discovery. But beyond the specific concepts we've discussed, I think there's a broader lesson here about the importance of curiosity
Right.
and the willingness to delve deeper into seemingly complex ideas.
I couldn't agree more. This deep dive has shown me that even the most intimidating mathematical topics
Yeah.
can be broken down and understood
Right.
with a little effort and a lot of curiosity.
That's the spirit. And it's that curiosity that drives innovation and leads to breakthroughs in all fields, not just math.
Right.
So never be afraid to ask questions, explore new ideas, and push the boundaries of your understanding.
Well said. Now, before we say goodbye,
Yeah.
is there one final thought, a nugget of wisdom that you'd like to leave our listeners with?
Here's something to ponder.
Okay.
We've seen how math can be used to analyze patterns in nature, the stock market, even random events. But what about the patterns in our own lives? Are there mathematical principles at play in our decision-making, our relationships, or the paths we choose?
That's a fascinating question. It's like you're challenging us to apply these mathematical lenses to our own personal experiences.
Precisely. Perhaps there are hidden Fibonacci spirals or recurrence relations governing our lives that we haven't yet recognized.
Wow.
Maybe there's a Thumor sequence subtly influencing our choices. The possibilities are endless, and I encourage you to explore those ideas with the same curiosity and enthusiasm that we've brought to this deep dive.
What a thought-provoking way to end our exploration. I'm definitely feeling inspired to go out and search for those hidden mathematical patterns in my own life.
That's wonderful to hear. Remember, math is more than just numbers and formulas. It's a powerful tool for understanding ourselves and the world around us. So keep exploring, keep questioning, and keep diving deeper into the fascinating world of mathematics.
Thank you for joining us on this incredible journey through the world of Fibonacci sequences, binary codes, and random polynomials. We hope you've enjoyed this deep dive, and we'll be back soon with another exploration into a new and exciting topic. Until then, stay curious.